So we're finally ready to start talking about Bell's theorem, named after a physicist named John Stuart Bell, who came up with this theorem in the 1960s in response to Einstein, Podolsky, and Rosen's criticism almost 30 years earlier about the nature of quantum entanglement and what is really happening. Let's start by setting up our entangled system and quickly review the problems that Einstein and his colleagues raised. The idea here is that we have a two-particle state whose wave function is in a superposition, such that if Alice and Bob, each with their respective particle, were to measure spin in the z direction, they will always get opposite results. Now, we chose to write this using the z basis, but we could have equivalently written down the state in the x or the y basis, or really any other basis of our choice. We're going to write our state in the z basis, but again, it's actually a very general statement, and you can prove either by making use of symmetry or by doing a straightforward change of basis. You could prove that we could replace all the z's with x's or y's, and we would actually be describing the same exact quantum state. For the sake of simplicity, let's say that Alice and Bob have each chosen to restrict themselves to making measurements in the x and the z directions. Now, they're not going to collaborate about when they're going to perform each measurement. They're just going to choose in the moment which one to carry out. There are only a certain number of possible combinations of results that Alice and Bob can get, so let's tally those up. If Alice and Bob both choose to make a measurement in the z direction, there are only two possible outcomes. Alice gets plus and Bob gets minus, corresponding to the first part of our wave function, or Alice gets minus and Bob gets plus. On the other hand, if Alice measures spin in the z direction and Bob measures spin in the x direction, there are actually more options. Alice could find hers in the z plus or z minus state with a 50-50 chance each, but for each one of those, Bob could get either x plus or x minus. If we switch it around so that Alice measures spin in the x direction and Bob measures spin in the z direction, we get essentially the same thing. And the last possible set of outcomes occur when Alice and Bob both measure spin in the x direction, where they'll once again, just like when they both measured spin in the z direction, find that their measured components are always opposite each other, so that the total component of spin in that direction remains zero, consistent with our entanglement condition. From this chart, we can actually pick out two different patterns. If Alice and Bob perform measurements in the same direction as each other, then their results are perfectly correlated, or technically anti-correlated. They'll always get the opposite measurement of the other. On the other hand, if Alice and Bob measure spin in perpendicular directions, their outcomes are completely uncorrelated. They're random relative to each other. This shows that the outcome of the second measurement performed appears to depend on not only what the result of the first measurement was, but also on what the first experimenter chose to measure, spin in the x direction or spin in the z direction. And this is true whether Alice and Bob are standing next to each other or whether they're light years apart and there's no hope of communication between them or between the particles of their entangled system. The orthodox quantum mechanical interpretation of this, once again, is that these measurements constitute kind of a selection process, that our system is described by this wave function up here, and that a measurement of a part of our system constitutes a measurement of the whole system. So if Alice measures spin up in the z direction, then we select out this piece of our wave function. Therefore, Bob will measure as z minus. On the other hand, if Alice measured z minus, we've now selected out this piece of our wave function, so our state collapses, and Bob will now find z plus if he makes a subsequent measurement. And of course, we could make the same kind of argument if they make measurements in a direction other than the z direction. And note that this orthodox interpretation of quantum mechanics accepts that there is some non-local behavior here, which is to say that a measurement performed in one location on part of the system instantly affects the state of the entire system everywhere arbitrarily far away from the original measurement. This made a lot of physicists uncomfortable because it kind of seems to overturn something that was traditionally held to be true. And in 1935, Einstein, Podolsky, and Rosen wrote a paper where they asserted that the universe should exhibit what we now call local realism. Einstein's own words on this topic were, "But on one supposition we should, in my opinion, absolutely hold fast, the real factual situation of the system S2 is independent of what is done with the system S1, which is spatially separated from the former. To boil it down, Einstein, Podolsky, and Rosen were arguing that the superposition and the apparent strange non-local behavior exhibited by the system we were just discussing are an indication of the incompleteness of quantum theory rather than a reflection of the nature of reality itself. Or in other words, that the behavior we see here is not actually different from what we discussed with the red and blue marbles in a classical example of entanglement earlier, but rather that we just don't have all the information about what the initial state was. There is information that we either haven't measured or don't have access to. So it was put forward that we could complete our quantum mechanical theory by adding in so-called hidden variables. These hidden variables could either be properties or parameters describing quantum mechanical systems that we simply don't know about and don't know how to measure, or they could even be inherently unmeasurable, that it is literally physically impossible to ever measure or otherwise access these hidden variables, but nonetheless, there is some element of reality that is hidden from us that actually makes everything deterministic and behave very much in a classical sense, and that the observed probabilistic nature of quantum mechanical systems is merely a reflection of our ignorance of those hidden variables. This argument raged on for a solid 30 years, but it was really more of a philosophical argument. It didn't really affect the development of quantum mechanics as a physical model. This argument raged on for a solid 30 years, but it was really more of a philosophical argument. It didn't really affect the development of quantum mechanics as a mathematical model used to make predictions about experiments. The reason for this is that it was believed that hidden variable theories could be concocted in such a way that they would give the same predictions about experiments that we already had from our probabilistic model. The difference is that hidden variables would replace all the quantum weirdness by saying, listen, everything looks weird. It looks like there's superposition. It looks like there's probabilistic behavior. It looks like there are non-local effects. But in reality, these are just artifacts of the fact that we are ignorant about some portion of the properties of the systems that we're measuring and experimenting with and observing. And then in 1964, John Stuart Bell realized that local realism actually makes predictions that would be testably different from the predictions of orthodox probabilistic quantum mechanics. And it has to do with the correlations between the measurements performed on different parts of entangled systems. To demonstrate this, let's consider a simple example of a hidden variable theory. Traditionally, we would say that a particle cannot simultaneously have well-defined spin in the x and the z directions because the spin in the z direction and spin in the x direction are incompatible variables. They're related by an uncertainty principle and so on. But if we create hidden variables that behind the scenes dictate what's going on, we can actually get around that restriction and we can recreate this entire table of results. There are certain constraints that we do need to be careful to follow. For example, we know experimentally that we cannot simultaneously determine the x and z components of spin of a particle. Whether they are in reality well-defined or not, we cannot determine them simultaneously. One of the simplest hidden variable models that nonetheless reproduces the basic principles of quantum mechanics is as follows. Suppose that a particular particle, a spin 1/2 particle, maybe an electron or a positron or something, has the properties that if the z component to spin is measured, we will obtain a plus sign with certainty, and if the x component of spin is measured, we will obtain a minus sign with certainty. We would say that this particular particle belongs to the type z plus x minus. To clarify, I'm talking about a single particle here, not talking about, Alice's particle and Bob's particle. This is just one particle. And I'm saying that this particular particle has the type that if you were to measure spin in the z direction, you will get a plus sign. And if you were to measure spin in the x direction, you will get a negative sign. In order for this to be consistent with what we know about quantum mechanics, there have to be 3 other types as well. I also have to have an electron of type z plus x plus, and I also need to have a type z minus x minus, as well as z minus x plus. We know from experiments that if we have a particle whose spin we know in the z direction, and then we measure their spin in the x direction, we should get a x minus half the time and x plus half the time. And same if we reverse things and we know the x state and we measure the z state. Again, there should be a 50-50 split. In order for that to work, it implies that, generally speaking, each of these types of particles should be equally likely. For every particle of this type, there has to be a particle of this type. And for every particle of type 3, there has to be a particle of type 4. Additionally, we know that if I measure the spin in the z direction, and then I measure the spin in the x direction, and then I measure the spin in the z direction, I'm not guaranteed to get the same z component of spin that I started with. Once I measure the spin in the x direction, I know that I now have a 50 chance of getting either plus or minus in the z direction. And so this model has to reproduce that as well, and there are several ways of doing it. One way that you might think is kind of cheating is to say, well, the act of measuring spin itself can affect the state. And so if I measure the spin in the x direction of a type 1 electron, that can affect the state and turn it into a type 3 electron with the same x spin. So I know what the value of spin in the x direction is, but then when I make my subsequent measurement of z, I don't necessarily know what I'm going to get. The reason why that might not be so satisfying is what determines whether or not it switches and when it switches and how often it switches, and shouldn't it depend on the details of your experiment. Another way that we can do it is we can just make up a rule that determines how this happens. But I'm not going to make up a rule because it turns out that we don't have to. And everything we're going to do from this point, it doesn't matter what that rule is. Any rule you can think of is going to be consistent with the work that we're about to do, and that means all that matters is to say that we can break up our particles into these 4 types, and that through some mechanism that we don't even need to specify, we cannot simultaneously determine the x and the z components of a particular particle. Our chart of correlations between the measurements made by Alice and Bob on our entangled system can be completely reproduced using this model as long as Alice and Bob's particles are matched like this. In other words, every time our pion decays, it has a 25% chance of ending up in this pair, or this pair, or this pair, or this pair. And again, there can be some hidden property that determines under what circumstances each of these happen. For example, there could be different types of pions, and we don't know which kind of pion we have. But 1/4 of pions decay into this kind of entangled pair, and one decay into this kind, and so on. If you want, you can actually go through and you can verify that this list of correlations, including their relative probabilities, are completely matched by this. This first type corresponds to 4 different possible measurements. Alice measures z plus and Bob measures z minus, or Alice measures z plus and Bob measures x plus, or Alice measures x minus and Bob measures z minus, or Alice measures x minus and Bob measures x plus, and so on for the others as well. There is nonetheless a very important assumption here that's different from how we've been treating quantum mechanics so far. Let's say after a particular muon decay, Alice and Bob end up with the first kind of particle pair. If Bob chooses to measure spin in the z direction, Bob will get a minus sign no matter what Alice does. Alice's measurement, even if she performs hers first, has no effect on Bob's measurement. And so you can see how this hidden variable theory incorporates Einstein's locality. There is no instantaneous effect over large distances. Nothing Alice does affects anything about the state that Bob is dealt, or vice versa. But rather, Alice and Bob's measurements are independent of each other, and they are connected by this hidden variable, this hidden information that was part of our system to begin with, that Alice and Bob simply are unaware of. And in that sense, this hidden variable version of entanglement is not really any different from the red and blue marble, where Alice and Bob didn't know which marble they had, but it was nonetheless determined even before they opened their boxes. Such an interpretation of quantum mechanics was very attractive because it meant we could still apply all of our, good old classical intuition for the way things work to quantum mechanical systems, and all the weird behavior is simply a consequence of our ignorance of the underlying systems that we're studying. And in fact, we could actually go back and we could apply this hidden variable theorem, again with some rule that prevents us from simultaneously determine the x and z components of spin of a particular particle simultaneously. And we could actually redo everything we've done since we started talking about quantum mechanics, and we would get all the same results. And so you might be thinking, well, what the hell? Why didn't we just do that to begin with? This is way less confusing than superpositions and other weird things. In order to see where this breaks down, we have to consider scenarios where Alice and Bob perform measurements of spin in directions that are no longer perpendicular to each other. So not just the x and the z and maybe the y direction, but maybe some direction that's somewhere between x and z, for example. So now let's suppose that Alice and Bob can rotate their measurement apparatus to measure spin along any three directions of their choosing. Let's call them A, B, and C. And once again, we can imagine that each of our particles belongs to a specific type, where that particle's type determines what value of spin you'll get if you measure spin in the A, B, or C direction. For example, we can have a particle of type A plus, B plus, and C plus. Now, in order for all our probabilities to work, there has to be an equal number of particles that belong to the type A minus, B minus, and C minus. Likewise, we can have a particle of a type A plus, B plus, C minus, and a corresponding pair, if you will, that's A minus, B minus, and C plus. And of course, we can keep going through the whole list of all the different possible combinations, but you get the picture. In the example of our entangled system, the two particles always have to come in these complementary pairs to ensure that if Alice and Bob, by happenstance or by choice, measure spin in the same direction, that they always get consistent results, that they're always opposite each other. And as you can see, there are 8 different ways for this to happen. And this column on the left that I've labeled population refers to the number of times, after a large number of trials, that each one of these particle pairs has showed up. It's important to note that this is not something that I've measured. It's not something that I can really measure, because in our experiments, we never know which type of particles we had. For example, if Alice measured A plus and Bob measured A minus, all that means is I know that we had one of these 4 combinations of particle types. I don't know which one it is, and I can't know. I literally cannot measure this information. The information is fundamentally hidden from us. That means that I can't measure N1, N2, N3, N4, N5, N6, N7, and N8. I don't know how many times each of those particular particle pair types have occurred, but as you're going to see, it's not going to matter. Now let's suppose that in a particular experiment, Alice measures A plus and Bob measures B plus. Take a few seconds, pause the video, and try to pick out which pairs Alice and Bob could have had. If Alice measured A plus, it means we must have had one of the first 4 states. And if Bob measured B plus, it could have been 3, 4, or 7, 8. And so the intersection of those is 3 or 4. So they might have had pair 3 or pair 4. Now I'm going to do something that's going to seem a little bit random, but bear with me. So first of all, these N1s, again, represent the number of times each of these particle pairs have occurred. And because they represent the number of times they've occurred, it means they're always greater than or equal to 0. That lets me write down statements like N3 plus N4 is less than or equal to N2 plus N4 plus N3 plus N7. We can also calculate probabilities. For example, what is the probability that Alice measured A plus and Bob measured B plus? Well, Alice's particle was A plus and Bob's particle was B plus, N3 plus N4 number of times out of a total number of trials of N1 plus N2 plus N3 plus N4 plus N5 plus N6 plus N7 plus N8. I can calculate the probability that Alice's particle is A plus and Bob's particle is C plus the same way, except this time the numerator is N2 plus N4. And I can do the same for Alice's particle being C plus and Bob's particle being B plus, where this time the numerator will be N3 plus N7. Based on those probabilities, if we divide our inequality on the left by the total number of trials, our inequality actually becomes a relationship between the probabilities of different combinations of outcomes on Alice's and Bob's particles. This might not seem like a big deal, But if you think about it, what we've just proved here is that any quantum theory based off of local hidden variables must satisfy this inequality for entangled systems. In other words, local realism predicts that this particular inequality has to hold true. This inequality is called Bell's inequality. So now let's compare this prediction to the prediction of standard quantum mechanics. That means we're back to good old superposition of states. So first of all, again, remember, now we've defined axes that are not orthogonal to each other. So for example, we're talking about measuring spin along an axis that we've labeled A and an axis that we labeled B. Forget about C for now. We can specify these two axes relative to each other by introducing an angle that I'm going to call theta AB. In order to compare this to Bell's inequality earlier, we need to calculate those same probabilities, this time using standard quantum mechanics. So for example, I want to know in this version of things, what is the probability of Alice measuring A plus and Bob measuring B plus? Now, if Alice's particle is in the state A plus, that means B's particle has been collapsed to the A minus state. In other words, Bob is measuring the spin in the B direction of a state that is A minus. And we're asking, what is the probability of that measurement yielding B plus as opposed to B minus? We've actually not analyzed non-orthogonal states mathematically like this before. However, we have done it before. If you think back to that simulation lab about the Stern-Gerlach effect, where I had you look at the probability distribution of the outcomes when the two Stern-Gerlach machines were oriented at different angles, you came up with a model to predict the probabilities. And if you look back at that, you'll see that you determined that the probability of finding a state A minus in the B plus state is equal to the cosine squared of the angle between those two directions divided by 2. The first thing to watch out for is this probability is not like this probability. The probability up here means the probability of Alice measuring A plus and Bob measuring B plus. This is what is the probability of Bob measuring B plus starting with the state A minus. Secondly, this angle theta is the angle between A minus and B plus, which means it's this angle, not the angle that I labeled theta AB, which means that we can rewrite this probability as cosine squared of pi minus theta AB over 2. And we can simplify that further to sine squared of theta AB over 2. Now we can go back to our probability up here on the left, which again is the probability that Alice measures A plus and Bob measures B plus. And that's equal to the probability that Alice measures A plus in the first place, times the probability that Bob measures B plus, given that he's starting with the state A minus, which is what we just found. The probability of Alice measuring A plus if she measures in the A direction is 1/2, because there's a 50-50 chance of getting spin up or spin down in any particular direction of an otherwise random state. And we just calculated the probability of the second term. And so we get that this probability is equal to 1/2 times the sine squared of the angle between the two directions divided by 2. You might be thinking, why does Alice have to come first? We could have actually done this the other way around. We could have said, assuming Bob makes his measurement first, what is the probability of Alice measuring A plus? We would end up actually doing essentially the same exact math, and we would have got the same exact answer had we assumed Bob's measurement happened first. It actually doesn't really matter which one you do. You're going to arrive at the same result. So now let's look at Bell's inequality and see what more we can do. We can follow the exact same process we did over here to calculate this probability on the left in order to find these two probabilities on the right. I'm not going to actually go through the math, but the result that you get is this. So here's the question. Do these probabilities that we calculated using traditional quantum mechanics satisfy Bell's inequality, which must be satisfied if the apparent randomness that we see and these non-local behaviors are going to be accounted for by local hidden variables? The answer is no. There are some values of theta that it's true for. For example, if we set all the angles to be equal to each other, then of course the left-hand side will be less than the right-hand side. But the inequality doesn't hold for all angles. For example, if theta AB is equal to pi over 2 or 90 degrees, and theta AC and theta CB are both 45 degrees or pi over 4, then this inequality is trying to tell us that 0.5 is less than or equal to 0.292. That is not true. What that means is that traditional probabilistic quantum mechanics is inconsistent with the notion of local hidden variables. It's inconsistent with local realism. This is the power of Bell's theorem. It tells us that we can perform experiments that can tell us whether or not local realism is, in fact, a property of the world. This doesn't really answer the question, though. This just tells us that the two different models make different predictions. And so experiment after experiment and after experiment has been carried out over the years, testing the validity of Bell's inequalities. Basically, we measure these different probabilities, these correlations, and we'll check, do they violate Bell's inequality or do they satisfy it? If our measurements consistently satisfy Bell's inequalities, it suggests that at the very least, local realism might be the case. But if our measurements violate these inequalities, it tells us that the universe is not locally real. So let's take a look. Bell's inequality can be converted into a computation of the extent of the correlation of the two states as a function of the angle between the directions in which the two observers are performing their measurements. And we see here that if the two observers are measuring in the same direction, which means there's 0 degrees between the two directions of their measurements, there is a -1 correlation. This is a perfect anti-correlation, which means that the results will always be opposite each other. If they measure in perpendicular directions, like the x and the z direction, then the correlation goes away entirely, just like we saw in the very beginning of this video. Then, if they measure their spins in opposite directions, the correlation becomes 1. And that's because if they're measuring in opposite directions, plus means opposite things for them. So if they both measure plus, but their apparatuses are in complete opposite directions, then their spins are actually opposite each other, and so once again we have 0 total spin. And then again it goes back, as you complete the cycle. This red curve represents the equality in Bell's inequality. So if the equality holds exactly, we expect our correlations to fall along this line. You'll see that the correlations match at 0 degrees, 90 degrees, 180 degrees, 270, and so on. In other words, the correlations between a local real model and a probabilistic model, or at least a non-locally real model, are consistent with each other for specific angles. And we saw that when we created our simple hidden variable model. We saw that it reproduced the correlations that we got originally for those particular angles. It's only when you look at the off angles, the in-between, where things start to go wrong. According to the inequality, if local realism held true, then our correlations should fall somewhere in this shaded region. On the other hand, the predictions of more traditional quantum mechanics that doesn't exhibit local realism is represented by this blue line, which clearly falls outside of the shaded region, except for the very specific 90-degree increment angles. So now let's look at some actual data. I won't go over all the details, but this dotted line over here corresponds to this blue curve over here. Note that 0 is here in this graph, right? There's no line to demonstrate it, but it's there. The purple dots represent the data. You can even see the error bars associated with the uncertainty of their measurements. And you can see that the data much more closely follows this blue, or this curvy line corresponding to the predictions of probabilistic or non-local real quantum mechanics than it does with the predictions or the requirements of Bell's inequality. It certainly doesn't fall within this shaded region. Moreover, the paper that I took this from calculated that violations of Bell's inequality were determined to within 18 standard deviations, which is insane. I tried to calculate the probability of that measurement corresponding to like random chance, like they just got unlucky with their data. But Wolfram Alpha, Mathematica, nothing of them will actually give me a number. Nothing can handle a number that big. Now that's not necessarily the whole story. Just because something has a really high degree of certainty doesn't mean there couldn't have been problems with the experiments. And that's actually, these experiments have been going on for decades and decades and decades, and they've always more or less shown the same result. However, there are all kinds of so-called loopholes, potential problems with experiments that could, if fixed, maybe change the results. And so you can't just go by the standard deviation. But nonetheless, the data consistently seems to show that our universe is not one that exhibits local realism, and that our universe has a more open mind than Einstein had. Now, there are some caveats that I need to mention, limitations of Bell's theorem. For one, we derived it based on the assumption of local hidden variables. Bell's theorem does not say anything about the possibility of non-local hidden variables. It is actually possible, or it seems to be possible, to construct a model of quantum mechanics with non-local hidden variables that is consistent with all of our other more traditional interpretations of quantum mechanics, as well as our experiments. That would probably still not be very appealing to Albert Einstein, because a large portion of his discomfort with quantum mechanics was its non-locality. But nonetheless, based on Bell's theorem and our experiments over many decades, it appears that our universe does not exhibit local realism. And while this has made many people, including many physicists, very uncomfortable in the past, and in fact even still today, it does appear to be the case. And I guess the universe just has a more open mind than a lot of people, including great people, including incredibly creative and brilliant people like Albert Einstein. Sometimes we get hung up on our ways. Sometimes we can't get past our own intuition. But the universe is not obligated to make sense to us and our limited human experience. It certainly doesn't answer to us, and the best that we can do is poke and prod at it and do our best to try to piece together how it actually works, no matter how strange that may actually be.